Okay, this is Professor Olness, and I wanted to take a moment to go through the tuning notes again and have that as a recording so you could review it at your leisure because this is going to be one of the key elements on exam number 2. So let me take a few moments to go through that. And let's see, so my annotation pen out. Okay, make sure that's correct. All right. Okay. And let's see. All right. Okay. So again, in this course, we're just gonna focus on four of the systems, although there are hundreds of them that we could focus on. And so the student notes, this was a student project a while back. They did a very nice job. So I'll be referring to that, and that's linked on the webpage under the general resources. So let me start off with the Pythagorean system. And you should know how it's defined, what are the pluses and what are the minuses of each system. So for the Pythagorean system, it's based on pure fifths. That's how we're set it up. And so here are the intervals that it gives us. The octave is always pure in all systems. That's a 2-to-1 system here. And the fifth is the 3-to-2, and then the fourth is an inverted fifth. So these two go together. If you have a good fifth, you'll have a good fourth. And then here's also the relation here. The octave is 1-to-2, the fifth is 2-to-3, and the fourth is 3-to-4. And again, you can use a harmonic series to get those. We will expect you to know those. You can either memorize those or you can work them out using the harmonic series that I sort of sketched out on the board that time. And so in a nutshell, down here, they have a very nice diagram that illustrates it. So here's the 2-to-1 octave, C to C. Here's the fifth, that's the 3-to-2. And then the fourth would be C to F, or equivalently G to C. And so that's how that goes. And you can see if you invert this 4-to-3, you get a 3-to-2. And yeah, so and if you put together a fourth and a third, 4-to-3 times a 3-to-2, the threes cancel. That gives you a 4-to-2, which reduces to 2-to-1. That's the octave. So this has a perfect fifth. And so what we want to do is use that to figure out what our third will be. And the way we'll do this, we will run through a cycle of fifths. We'll start with C, and then we'll go up a fifth. And they have this very neatly illustrated here. So they're going to figure out the Pythagorean third. And so what they do is they start with C, and they're going to go up a fifth. So that increases by 3-to-2. That gets us to G. Here's our G. And then we're going to go up another fifth. That's a 3-to-2 ratio. That takes us up here to D, up here. But that's in the wrong octave, so we need to drop this an octave. And so what we're going to do here in the magenta is drop that an octave. So we're going to multiply by half to get it down in the octave. We're now at this D, and now we go up a fifth. That gets us to this A. So here's that in green. We multiply the D by 3-to-2. That gets us the A. One more time, we go up another fifth. That takes us to the E up here. That's what's going on here in the red. But again, that's in the wrong octave. So we drop an octave shown in yellow here. That takes us down to the E. And if we put all that together, here they've calculated it out, but basically you take 3-to-2 times 3-to-2 times a half times 3-to-2 times 3-to-2 times a half. You multiply all that together and you'll get 81/64. And that's going to be our third. Now, this I will not have you do. This is a rather complicated calculation, and I will not have you do something like this, but I will have you do simple two-step calculations and illustrate that down below. Okay, so I just wanted to show you where this comes from, but I will not expect you to be able to do this on a test. But I just wanted to show how this comes about. Basically, you say I've got an octave and a fifth. How do I get from that to get my third? And you can use the cycle of fifths. Okay, and so here's what we get. We get the E is a 81 over 64. Okay, and you could do something similar to figure out how to get the half steps, the whole steps here and the half steps here, major second, minor second. And so in this case, we use the ideal 9 to 8. That's the ideal major second and major second here. But now the minor second is this horrendous 256 to 243. And so again, let's step back and take a look at this for the Pythagorean system. What are the positives? What are the negatives? It has a perfect octave, a perfect fifth, and then the fourth comes automatically. And we're imposing a perfect whole step, major second, but the thirds are terrible. 81 over 64, that's very close. 80 over 64 would be a 5 to 4 ratio. That would be the ideal third, but it doesn't work out. And this also, that minor second is horrible. And again, the rule of thumb here is that the smaller numbers give you better intervals. So things like 9 to 8 or 4 to 3 or 3 to 2, those are good intervals. And things like with big numbers, 81 over 64 or something like that are bad intervals. So it has nice, very good whole steps. It's got a very wide third. It's got a bad half step, and so that's going to give us some problems. So in a nutshell, that is the Pythagorean theorem. Here is the relationship in sense, and on the fourth page of this, I have a comparison in sense. But so we can see here, there are 1,200 cents in an octave. So we go through the 12 chromatic steps, and and that's, each chromatic step evenly divided is going to be 100 cents, and 12 of those is 1,200 cents. Okay, and here's our fifth. The ideal fifth is 702 cents. Okay, the ideal whole step is 204 cents. And so I have 204 cents here, 204 cents here. Those are ideal whole steps. I put that together, I get 408. That we're going to see that turns out to be too wide. So it has a good whole step, but a bad third. Okay, and also this relationship between the E and the F, that's also a bad interval. The other thing is you could take this cycle of fifths and go all the way around through all the 12 chromatic steps. And if you do that, what you find is when you start from C and go through all the 12 chromatic steps, going up by a factor of 3 to 2 and then dropping the octave where you need, what you find is when you come around, you're off. And in fact, what you see is that the ideal fifth is 702. And for the equal tempered scale, it would be 700. So it's 2 cents high. And what happens is when you go through 12 of those, 2 cents times 12 is 24 cents. What you find out is that the B sharp you get after you go through the cycle of fifths is 24 cents too high. And remember, 100 cents is a half step between, that's roughly between something like an E and an F. So you're a quarter of a tone high. That's quite noticeable. And that's what we call the Pythagorean comma. Comma, you can think of that as the air in the system. So this is the Pythagorean air that comes about going through, trying to use the cycle of fifths to get back to the C again. Okay, so again, what are the problems? It has a bad third. Okay, it has a bad minor second, and then if you try to use the cycle of fifths to come around again, your B sharp is not going to equal C as it should. And again, let me scroll up a little bit and just repeat that. You can see it here. You've got a very nice whole step, very nice whole step. The third is bad. This minor second is bad. And then if you did the cycle of fifths to go from C 12 octaves up to, or 7 octaves up to C, you would be off by the Pythagorean comma of 24 cents. So that's a Pythagorean scale. So how can we improve that? And again, this is just one example, but we're going to use just temperament. And the idea here is we would like a good fifth and a good third. And as Professor Baker mentioned, the early Gregorian chants and the early music sort of focus on the fifth, but later composers decided they wanted to take advantage of the third. And something like the Pythagorean tuning, that just wasn't possible. So we're going to extend this and not only use the fifth, but we're also going to try to get a pure third. So here are the ratios. The octaves 2-1, and the fifth and the fourth, those come together. Those are reciprocal of one another. Okay. And then what we're going to add here is the third. And the ideal third is a 5-4 ratio. And what we're going to find is we can do that by, we get the ideal major second 9-8, but we're also going to see the appearance of this 10-9, which is also a major second. But remember, lower numbers are better, so we prefer the 9-8. The 10-9 is pretty close. Those are pretty similar. Work it out in your calculator. You see how close they are. But we prefer the smaller numbers. That gives us better harmonies. And then we also, for the minor second, instead of getting that horrendous ratio, we get a very nice 16-15. So it looks like, from that, it looks like things are perfect and we can actually use this to solve all our problems, but let's try it out. So what we find is if we say the fifth has to be perfect, okay, so here's the fifth, that's C to G, and that's, in terms of cents, that's 702, or that would be a 3-2 interval. Okay, that's good. All right. And now we want the third to be good. So we want the third here is C to E. We want that to be a 5-4 interval. And to do that, there are a number of ways to approach this, but what we're going to do in the just system, we keep the ideal 9-8 going from C to D. But how do we get from D to E? If C to D is determined to be 9-8, and this is determined to be 5-4, it turns out, and this is the type of thing I will ask you to work out. It turns out that D to E turns out to be 10-9, 10-9, not 9-8. And so here we have the ideal second. Here we have a less ideal second. Okay, so it's close and it's a nice ratio, but not quite. And then also, if you work it out, you find out that the E to F, the minor second, is a very nice 16-15. So, it's a compromise, but it's not too bad. All these numbers are, you don't see those horrendous large numbers like we did in the Pythagorean case, but you have these unequal whole steps. And that's going to be very unsettling. If you start doing scales and things like that, you're going to notice that immediately. You do get the very nice minor second, but the fact that they have unequal whole steps really makes that unacceptable for use. And then they've worked out some intervals here. For example, if you want to work out the GA interval to show that's 9-8, that's worked out here. So actually, one tip here, there's a missing step, but to do that, they use the fact that C to G, that's a fifth, so that's a 3-2 relation. And where did this 5-3 come from? What they did was they used the fourth. They went C to F. Okay, that's a 4-3, and then they used the 5-3 third. So this 5-3 actually comes from a 5-4 and a 4-3. And then putting those together, you have 5-3 and then 3-2. This minus is, should think of that as a divide. And when you should think of that as a divide. And basically here it is, it works out like this, and basically you get the 10-9. Okay. And then let's see, the other calculation, the minor second calculation, if you know the fourth is a 5-4 and the third is a 5-4, and you know the fourth is a 4-3, again, you work that out and basically think of this as a divide here, and you get the 16 to 15 second. And I'll go through those calculations in a little bit. Actually, let me do that. Let me switch over to that now and get my cursor there. Okay. And make this come on, make it a little bigger. Okay, I can't see. Why is that not getting bigger? Sorry. It looks like I'm at the maximum resolution. So, okay, so here's some example calculations, and this is the kind of thing I expect you to be able to do. So, for example, if I want the ratio of E to C, if I want that ratio, I want to figure it out, but I may not know it. If I know the ratio between E and D to C, I can think of this as fractions. And you notice there's one D downstairs and one D upstairs. And so basically those cancel, and you see in the end that will equal E to C. And so let's pretend that both of these are the ideal whole steps. So these are 9 to 8 and 9 to 8. And then what I do is I multiply those together, and this tells me 9 times 9 is 81, 8 times 8 is 64, and that's where I get that terrible 8164 that I had in my Pythagorean case. Okay, now that is very close to, if that were 80 over 64, that would reduce the 5/4, which is the ideal third. So it's pretty close, but not ideal. And this is what we have in the Pythagorean system. In the just system, what we do is we cheat. And for the E to, I should have put this in the opposite order. For the C to D, actually, we have the ideal 9 to 8. And for the E to D, we have the 10 to 9. Sorry, I reversed those. And now if you look closely, you see there's a 9 upstairs and a 9 downstairs. Those will cancel out, and I'm left with 10 over 8, which reduces to 5/4. And so this is what happens in the just system. We cheat on the second, we cheat on that E to D interval, we make that a little bit narrower, and that gives us the ideal 5-4 ratio. So these are the kind of calculations I do expect you to be able to do, and we'll do some more examples. We'll do some more examples in class. So let me go back to the notes here, and in those examples, I was sort of going up, and so I was multiplying. In this example, when you're doing, you go up and then you go down, the minus sign you should think of as a division here. But actually, if you write it out in terms of notes like this, making sure you always be aware of which note is larger, and then use that to follow which number is larger, it just works out very easily. So we'll do some more examples like that. So let me recap for the just temperament. So what we've tried to do is cheat and get both a pure fifth and a pure third. Okay, and we can sort of get that. That's the good thing. It has a good fifth and a good third, and of course the fourth goes along. If there's a good fifth, there's also a good fourth. But we have unequal whole steps, and that just won't work. So you have unequal whole steps, you do recover a decent minor second, but this is more a theoretical scale. Nobody's going to actually tune something like that. So that's how that goes. And so those are tunings. Those are tunings where we have exact ratios. Exact ratios. But now let's go to a compromise system, and that's a temperament. And so mean tone tuning, but it's really, I'm going to cheat here. And what we want to do is we decide that, we really like those pure thirds. So if you want to score your voices in thirds, you really need a good third. And what you realize is that the fifth is pretty close. What we did in the Pythagorean system, we did the cycle of fifths to get to the E. We went C to G, G to D, D to A to E. So we did, 4 steps going around the cycle of fifths. And the E that we found it turned out to be 22 cents too wide. And let me scroll down to the bottom where I have all the comparisons here. And all right, I have all the comparisons here. So let me get, so here's our E. This is our third. Okay. And so with the Pythagorean, we found out the E was too wide. That was the 81 over 64. And with the just, what we found is that is the ideal 5-to-4 ratio. So this is what we want. We really want 386 cents. If we, in the Pythagorean, we got 408 using the cycle of fifths. And the difference between this is 22 cents. So what we can do, we realize that, well, our fifth is 702. So what we can do is I'm going to squeeze the fifth. I'm going to take that 22 cents and going through my cycle of fifths, going through my cycle of fifths, let me get back. As I go through my cycle of fifths, what I'm going to do, if I go through the cycle of fifths, I get 22 cents too large. And so I'm going to take that 22 cents and divide it up between each of these 1, 2, 3, 4 steps. So 22 over 4 is 5.5 cents. And so what I'm going to do is I'm going to squeeze all of these fifths. The ideal fifth is 702. I'm going to squeeze those by 5.5 cents. And so I'm going to make those fifths 696.5. They're just going to be a little bit more narrow. And then when I go through my cycle of fifths, I get the perfect value for E instead of being too wide. All right. So we're going to sacrifice the fifth to get a good third. Okay. And here's the calculation. Not going to expect you to do this, but you come out with this and you have to subtract, you're up 2 octaves. So an octave is 1,200 cents. So you have to subtract 2,400 cents. And then, and then what you're left with is 386 instead of 408. So maybe we should have added minus 2,400 here to get 408 and 386. Okay. And the difference you see is 22 cents. Okay. So that's what we're going to do. And here are the intervals. Okay. Here are the intervals marked out. We have the perfect octave, 1,200 cents. And we have the perfect third, the 5-to-4 third, that's 386. Okay. And the fifth, we're going to sacrifice. We squeeze that just a little bit, so that's 696.5 instead of the perfect 702. All right. And so here's our perfect third, 386. That's a 5-to-4 ratio. And now the question is, how do we get the D? How do we get the whole step? And what we're going to do there is we're just going to put the D halfway between the C and the E. Okay, and that's why it's called a mean tone, because we're going to put the D at the average point between the two. So if you take 386 and divide by 2, you get 193, and that's where it comes out. Okay, all right. And so that's the setup. And we're not going to derive. There are other intervals here. We're not going to go in details about those. So just to recap, in the mean tone system, we sacrifice the fifth just a little bit to get a good third, and then we use the average value of D so that we have equal whole steps. So we have equal whole steps. We have a good third, not a bad fifth, but not a perfect fifth. And of course, because the fifth and the fourth go together, that means the fourth is going to be off a little bit. Okay. And so this is a temperament, we're sort of tempering things or making approximations or compromises to do this. And so that's another approach. Okay. And then finally, the last system we're going to use or discuss is the equal tempered system. And that is here. And in the equal tempered system, what you do is you just say the octave is 2 to 1. And I'm just going to, divide that very evenly among the 12 chromatic tones. And so I'm going to space those equally. And so, I put those all 100 cents apart. So there it is. And it goes from 1 to 1200. Okay. And let's compare how well the equal does to the ideal tones. So let's start over here with the Pythagorean. Okay. And remember, for the Pythagorean, the fifth was perfect. So a perfect fifth is 702. And also you see the just also has a 702. And how does the equal do? Well, it's 700. That's pretty darn good. You're going to have real trouble noticing the difference between 702 cents and 700 cents. Okay. And that means if the fifth is pretty good, the fourth is also pretty good. All right. So this is 2 cents above 700. The fourth is 2 cents below 500. So here's the equal tempered fourth. And here, both the Pythagorean and the just are 498. And remember, I said the fourth and the fifth kind of go together. If I have a good fifth, I'll have a good fourth because it's just an inverted one. The fifth is 3 to 2, and the fourth is 3 to 4. Okay. So we have a view there. Let's take a look at our mean tone on the fifth. So the mean tone, what we did there was, instead of taking the 702, what we did is we squeezed that by 5.5 cents. So if you take 702 and subtract 5.5, you get 696.5. And so it's not too far off the 700, but it's not bad. Okay. And then correspondingly, the fourth, we've actually rounded this. I should take off another half here. But you see, it's okay, but it's not perfect. So that's a compromise. All right. So that's where these things stand in terms of the fifth. Let's move to the third. So here's the third. And which has the good third? Well, the just system. In the just system, we decided we really wanted a good third. So we have a good third here, but we also had a good fifth, but we had a sacrifice on the whole steps. I'll get to that in a moment. So this is a good third. And also the mean tone has a good third. So 386 is a good third. Now, here's the Pythagorean, okay, and that's that 81 over 64. That's a very wide third, very wide third. And the equal, the third is not so good, but it is better than the Pythagorean. So, the third is off by quite a bit. And again, if you have, good sense of pitch, you certainly notice the third. That one is certainly noticeable. And again, there's a 22 cents difference between the two. And we took that 22 cents and divided it by 4 to get that's how we use that to define the mean tone to get the 5.5 cents. So that's the third. These two have good thirds. This is a pretty bad third, and equal is sort of bad, but not as bad as the Pythagorean. Now let's look at the whole steps. Okay, so here's the whole step, the D. All right, and now this 204, that is the perfect 9-to-8 ratio. That's very good. Okay, and actually the equal temperament, that's not too far off. It's only 4 cents off at 200. And here's the mean tone. Okay, and we had a ideal third, and if we go right in the middle of that, remember we took this and divide by 2. Here it is, and that's where it is. And so it puts it low compared to the ideal 9-to-8 ratio, but it does give you equal steps. There's 193 cents between these two and 193 cents between those two. Okay, and again, those are the compromises you make. Okay, and so you can sort of see the equal, it spreads things out very uniformly. If I transpose, if I transpose that from one key to the another, in principle, it doesn't matter at all what key I play. So if I do Bach's well-tempered clavier, I could transpose any one of those 24 preludes and fugues, well, actually 24 times 2, into any other key, and it would sound just the same on an equal tempered instrument. Now, of course, for orchestras that, we'll get to that when we do go to the strings. There's a reason the orchestras favor certain keys, and the reason wind instruments and bands, which have a lot of B flat instruments, favor other keys. But we'll get to that later. And so, again, let's just kind of go through, and we see for the equal tempered, the whole step 200 versus 204, not bad. The third 400 versus 386 is ideal. That's not so good. The third is one of the weaker ones. The fifth 700 versus 702, pretty good, pretty good. And so, for modern things, we typically use equal temperaments. And it works well for a wide variety of music. You can transpose, and it's just fine. And we'll talk about this later, because actually on campus we have both the Caruth organ and the Perkins Chapel organ. The Caruth, I believe, and we'll double check with Professor Baker, I believe the Caruth is tuned in equal temperament, and the Perkins Chapel, at least the old one, was tuned in a temperament, but not equal. So within 100 feet of within 100 yards of each other in campus, you have both an equal and a non-equal tempered organ. So that is the overview. And again, I'll just flash this one more time, but sorry, let me pull that up. And these are the kind of calculations I expect you to be able to do. And so, we can see here, in one case we get the terrible 81/64. In the other case, we get the very nice 5/4. And those are the simple things I will expect you to do. I will not expect you to go through the cycle of fifths as we did there, deriving them, but it's good to know where these come from. And again, coming back here, just to recap, the Pythagorean tuning, that's based on the pure fifth. That's the important interval there. And the deficit is the lousy third and the lousy half step, and the Pythagorean comma, the 24 cents when you go through the cycle of fifths. Just temperament is based on the pure fifth and the pure third, but to get that, you have to sacrifice. You have these uneven half steps, which is really not practical for playing. And then the mean tone tuning, that's an approximation. We're going to cheat on the fifth to get a good third. Okay, and then we use a mean tone. We use an average to get the second, so that's off. We do have a good third. The fifth is close. The second is off, but it's equal, and so that's a compromise. And that's characteristic of many of the temperaments. And when we go to visit David Brown, he can discuss some of that with you. I will finish there, but be glad to have questions in class. And we'll have certainly one more lecture on this to follow up on this. But these are the kind of things I expect you to be able to do. Hope that was useful, and we'll see you in class. Thank you.